In the first problem, we're working with graphs and properties of graphs like increasing and decreasing, and also with transformations of functions. In the first question, we're talking about where the graph is decreasing, and that's a simple concept. We can see the graph decreases basically when you look left to right whenever the y values are falling. The bigger difficulty that people have is expressing that answer using interval notation. Traditionally, when working with functions, we describe locations on the graph by just indicating the x-coordinate. So if we're trying to indicate a range of values on the graph, we want to do that with interval notation. So the first interval where the graph is decreasing is through here, and we can see that that happens for all values of x up to here. So that's up to -2. So in interval notation, we would write -infinity to -2 as the interval on which the function is decreasing. We also see the function decreasing on this region, and so that starts happening when the x value is -1 and ends when the x value is about 1. So we add to that the graph is also decreasing for values of x from -1 to 1. So the interval notation allows us to express a range of values of x, and then the values of x indicate points on the graph. The related question of where there are local maxima and minima comes from the same picture. Your definition of a local maximum is a place where the graph stops increasing and starts decreasing, and the definition of a local minimum is where the graph stops decreasing and starts increasing. So once I've labeled the points where the graph changes direction, then I've essentially labeled all of my local extrema. So the local minimum, there's a local minimum here and a local minimum here. So I want to express that as points. So I'll say I have a local min at 2 points. One point is -2, comma, whatever that y coordinate is. Maybe it's -3, -3 and a bit. And there's another local min when the x coordinate is 1. And when the x coordinate is 1, the y coordinate is about -5.5. For the local max, I'm looking at a place where the graph changes from increasing to decreasing, and that'll just be here, and we can see the x coordinate here is -1 and the y coordinate is about -3. The last part of this question talks about a transformation, and you can see in this expression that we're actually doing several transformations to the graph. And to get the order right, we just really want to think about order of operations. In this expression, the x plus 1 is inside the parentheses, and so that would be the thing we would do first. So the transformation corresponding to replacing the x with an x plus 1 is that there's a shift to the left by 1 unit. The next operation in the order of operations is this multiplication. That multiplication, the 3 times there, that's 3 times the result of f of x, and so that's 3 times the y coordinate. So that's a scaling in the y direction by a factor of 3. And then finally, the last operation is this -2, but again that's happening to the outputs outside the parentheses, outside of the f notation. So the outputs, remember the y coordinate, so the subtract 2 is shifting the graph down 2. So that's a change of -2 in the y coordinate. So once we've decided those are the transformations, then we can really just take our original point, this -1, -3, and apply each one of these transformations in that order. So the first transformation, remember we said, was shift to the left 1, so that'll shift -1, 3 to -2, -3. Sorry, -1, -3 to -2, -3. The second operation we said was scaling the y coordinate by a factor of 3. So multiplying the y coordinate by a factor of 3. And then finally, so this is 2. Finally, then -2 is shifting the graph down 2. So in other words, we're subtracting 2 from the y coordinates. So the final result of all those 3 transformations is that the point that was originally at -1, -3, which is here, is going to end up with coordinates -2, -11. In part 2, we're looking mostly at composition of functions, and along the way we're reminding ourselves about the meaning of domain and the connection between the points on a graph and evaluating the function. In part A, we're simply rewriting g of f of x as g of f of x, and as we said in class, working inside the parentheses out. First, inside the parentheses is f of x. We know from above that f of x is really x minus 4, so instead of g of f of x, I have g of x minus 4. And the rule for g is that g takes the square root. So if you do g of 7, you'd get square root of 7. G of 4 is the square root of 4. So g of x minus 4 just means square root of x minus 4. The domain of this function can be seen by just tracing the value of x that you're trying to put into the function all the way through that evaluation process. If I were to pick a value of x and put it inside the parentheses here, the first thing that happens to it is that 4 gets subtracted from it. And there's no number that I could use where subtracting 4 is going to cause an error. So there's no problem with that. However, in the next step, I'm supposed to take the square root of that value. And so we know that if we take the square root of a negative number, we're going to get an error on our calculator. So in order for this to not give us an error, we need x minus 4 to not be negative. We need x minus 4 to be at least 0. And if we rewrite that, that means that x is at least 4. So in order for this function to not throw an error, we have to have a value of x that we're using that's at least 4. So in interval notation, we would use the square bracket because we want to include 4, and then to infinity. F of g of x is a different function. If we do one step at a time again, now instead of g of x, I know g of x is the square root of x. So instead of f of g of x, I'm using f of the square root of x. And f is the function that when you put something in, 4 is subtracted. So when you put square root of x in, 4 should be subtracted. So this is the rule for f of g of x. Take the square root of x and subtract 4. In this process, the only time we might get an error is in this first step. If in that step I used a negative value of x, I would get an error before I even had a chance to use f of anything. So I know from that step that x has to be at least 0. In this final step, subtracting 4 from the answer, that's never going to cause a problem. So my domain is going to be all the numbers x that are at least 0. So in interval notation, my domain would be written closed interval, because we want to include 0 to infinity. Finally, we want to give coordinates of any 3 points on the graph. This is much easier than you would think. It's not really asking for a whole lot. We know that y is g of f of x. And the idea of this question is just to remind us that when you're drawing picture points on the graph, what you're really doing is using input-output pairs for the function. So if you want to find 3 points, just pick 3 different values of x for inputs. So if my input is x equal 4, notice that that's the smallest number I could have used. We're using this function, g of f of x. So I know the domain is x greater than or equal to 4, or all the numbers from 4 to infinity. So 4 is the smallest input I could possibly use. If I use that, then my output is just the value that I get by putting 4 in for x into the function. And again, we're using part A up there. So the output will be the square root of 4 minus 4, or the square root of 0. So if input's 4, output's 0. If input is 5, output is the square root of 1. And if I don't want to deal with any kind of ugly numbers, I could just skip next to the next number that will give me a nice answer, x equals 8. Because I know if I use 8, then I'll have the square root of 8 minus 4, which is the square root of 4, which is 2. So the 3 points that I could plot are 4, 0, 5, 1, or 8, 2. These are all 3 points will be on the graph of the function g of f of x.